AI is accelerating every single day. But what if the real limit of AI is not the algorithm? What if it is the chip? For more than 50 years, the semiconductor industry relied on a formula that seemed almost unbeatable. Make transistors smaller. The chip becomes faster, cheaper, and more energy efficient. That formula gave us smartphones, cloud computing, supercomputers, and the massive AI models we see today. But now, that formula is reaching its limit. The light used to print chips is becoming too large for the tiny features it needs to draw. Electrons are beginning to leak at the scale of just a few atoms, and even lithography machines that cost hundreds of millions of dollars cannot keep pushing Moore's law forward forever using the same old approach. So where will the next big leap in chip making come from? A bigger machine? A more expensive factory? Or a much bolder idea? Let the material organize itself and build part of the chip from within. If that works, the race between Intel, TSMC, Samsung, and Nvidia will not just decide who can make smaller chips. It will decide who controls the cost of AI, the power of supercomputing, and the future of the digital economy. And to understand why this matters, we need to start in one very specific place: Arizona. In the middle of the American desert, Intel and TSMC are not just building factories. They are fighting for control of the infrastructure behind the AI era. TSMC is taking the safer path: high yield, stable production, global customers. Intel is taking a much bigger gamble: new transistors, new power delivery, new lithography, and an ambition to bring advanced chip manufacturing back to the heart of the United States. But the biggest question is no longer who can make the smallest chip. The real question is this: who can produce enough powerful, affordable, and reliable AI chips for the entire world? Because in the AI era, chips are no longer just components. Chips are power. Whoever controls chips controls the cost of AI, the speed of supercomputing, and the technological position of nations. But before we can ask whether Intel or TSMC will win, we need to understand the root problem. Why can't chips keep getting smaller forever? Everything starts with the transistor. A transistor is a tiny switch that powers every modern chip. It processes data, images, autonomous driving systems, and even AI models. For decades, the semiconductor industry only had to keep shrinking those switches. Smaller transistors meant faster chips, lower power consumption, and cheaper computation. That was the foundation that allowed AI to explode. But as transistors moved down to just a few nanometers, the chip industry hit a physical wall: light. Chips are made by using light to print circuit patterns onto silicon. But when those patterns are only a few nanometers wide, light starts to become too large for the job. It is like trying to paint a strand of hair with a wall painting brush. You can make the brush more precise, but it is still the wrong tool for drawing something that small. In chip making, that can turn into a disaster: a broken line, a missing contact, a leaking transistor. A single atomic level error can ruin an entire chip. To push past that limit, the semiconductor industry built one of the most extreme machines ever created: EUV, extreme ultraviolet lithography. It is one of the most complex machines in the world. EUV uses light with a wavelength of about 13.5 nanometers to print incredibly small structures onto silicon. Thanks to EUV, Moore's law was able to survive for several more years. But the most astonishing part is how EUV creates light. Its light source is not a bulb, it is a controlled explosion. The machine fires lasers at tiny droplets of molten tin inside a vacuum, turning them into plasma hotter than the surface of the sun. That plasma generates EUV light again and again, with almost unbelievable precision. Thanks to EUV, chips kept getting smaller and more powerful. But now, even EUV is starting to hit its own limits. At the scale of just a few nanometers, light no longer behaves like a smooth stream. It arrives as individual photons. If one area receives slightly more photons and another receives slightly fewer, defects can appear. A broken line, a missing contact, a leaking transistor. Chip makers can increase the EUV dose to reduce errors, but then the machine runs more slowly. Wafers become more expensive. AI GPUs become more expensive. Data centers become more expensive. And eventually AI itself becomes more expensive. That is the new paradox of the chip industry. The harder we try to use light to draw with perfect precision, the more expensive everything becomes. So what if the next breakthrough is not about drawing smaller patterns? What if, instead of forcing light to do everything, we let materials build part of the structure themselves? This is where DSA comes in: directed self-assembly. The idea is simple, but extremely bold. Instead of using light to draw every tiny detail, EUV only creates a guiding template. Then, the material arranges itself. DSA uses block copolymers, which are molecules made of two parts that do not like to mix with each other. When heated, these molecules naturally organize into extremely regular nanoscale patterns, lines, dots, cylinders. In simple terms, the material builds the shapes that chip makers need. But in semiconductors, having the right shape is not enough. It also has to appear in the exact right place. That is why EUV creates the guide first. Then DSA uses chemistry to complete the smaller, sharper, and more uniform details. This is the breakthrough. DSA does not replace EUV. It helps EUV go beyond its limits. Light no longer has to do everything alone. The material helps finish what light can no longer draw reliably. And if this technology works at large scale, it will not just change how chips are made, it will change the economics of AI. DSA matters not only because it could make chips smaller, it matters even more because it could make chips cheaper. In semiconductors, success is not about making one chip in a lab. Success means producing millions of chips with low defects, high throughput, and costs low enough to make business sense. That is why yield is the number that matters most. High yield means a factory makes money. Low yield means a factory burns money. If DSA reduces the amount of EUV exposure needed, machines can run faster, process more wafers, and lower the cost of each chip. For AI, that means cheaper GPUs, cheaper data centers, and lower training costs for AI models. But DSA is also a major gamble. At the angstrom scale, one tiny impurity, one small misalignment, or one self-assembled region forming in the wrong place can ruin an entire wafer. So DSA is an extremely difficult test. If chip makers can control it, it could open the door to a new era of chips. If they fail, it could turn the production line into a defect-generating machine. But DSA only solves part of the problem. For chips to truly move into the next generation, something even bolder is needed. The chip itself has to be redesigned. That is where Intel 18A comes in. Intel 18A is one of the biggest gambles in the modern semiconductor industry. Intel is not just upgrading one feature, it is changing two foundational parts of the chip at the same time, the transistor and the way power is delivered into the chip. The first major change is ribbon FET. For years, the chip industry used FinFET transistors. In a FinFET, electrical current is controlled from three sides. But as transistors become extremely small, this design becomes harder to control and more vulnerable to leakage. Ribbon FET moves to a gate all-around architecture. That means the gate surrounds the entire channel. As a result, the current can be controlled more precisely, leakage can be reduced, and transistors can continue to shrink. But the more radical change is power via. In traditional chips, signal wires and power wires are both routed through the front side of the chip. That creates congestion, interference, and power loss. Power via flips that architecture. Signals still travel on the front side, but power is delivered from the back side of the wafer. In simple terms, Intel separates the data path and the power path into two different layers. The result is less interference, lower power loss, and more room for signals. This is not just a technical upgrade. It is Intel's attempt to rebuild chip architecture for the AI era. But that is exactly why 18A is also a survival test for Intel. On paper, backside power delivery should make chips faster and more energy efficient. But to make it work, Intel has to flip the wafer, thin the silicon, and create incredibly tiny connections to the transistors. A single atomic level error can disrupt the entire process. So Intel does not just need to prove that 18A works, it has to prove that 18A can be manufactured at scale with high yield, reasonable cost, and enough reliability for customers to trust it. And this is where TSMC has a major advantage. TSMC only manufactures chips. It does not directly compete with Apple, Nvidia, or AMD. Intel is different. Intel wants to be a foundry. It also sells CPUs, and it competes in data centers and AI. So Intel's challenge is not only to beat physics, it also has to overcome market skepticism. If Intel Foundry becomes a reliable second option after TSMC, especially as demand for AI GPUs keeps exploding, the balance of power in the chip industry could begin to shift. And this is what makes the race bigger than Intel. It is not just about whether one company can make a comeback. It is about whether the world gains another major center for advanced chip manufacturing or continues to depend too heavily on one dominant ecosystem. So what does the next chip breakthrough is not a machine really mean? It does not mean machines no longer matter. EUV, high-NA EUV, and factories like Fab 52 are still the backbone of the semiconductor industry. But the era of relying only on bigger, more expensive, and more precise machines is approaching its limit. The next breakthrough will belong to the companies that know how to combine three things: machines, materials, and chip architecture. DSA allows materials to organize themselves. Ribbon FET gives transistors better control over electrical current. Power via delivers power from the backside of the chip. But none of these technologies matter unless they can be manufactured at scale with high yield and low enough cost. In simple terms, the future of chips is not just about drawing smaller circuits. It is about controlling matter at the atomic scale in a smarter way. That is why this race matters. Intel is betting on bold reinvention. TSMC is betting on stability and execution. Samsung is looking for a chance to break through. And Nvidia, Apple, Microsoft, Google, and the entire AI industry are waiting to see who can supply enough chips for the future. Because the next chip will not just decide how much faster our phones or laptops become, it will decide the cost of AI, the speed of supercomputers, the future of autonomous vehicles, national defense, and the technological power of nations. The next chip breakthrough may not be a machine. It may be a new way to build matter at the atomic scale. And whoever masters that could master the next wave of AI. So what do you think? Can Intel return to the front line of semiconductors? Or will TSMC keep its crown through yield, experience, and customer trust? Leave your thoughts in the comments below. And if you found this video helpful, hit like, subscribe to the channel, and share it with anyone interested in AI chips and the future of technology.